Hello there, and welcome to the Sleep Science Calm Stories. I'm so glad you found your way here tonight. Wherever you are in the world right now, you might be settling into a quiet room, or lying comfortably in bed, or simply letting your mind slow down after a long day. The outside world can move very quickly. Messages arrive, clocks tick, and the small details of daily life ask for attention. But tonight, we're going to step into a very different rhythm. Tonight's journey takes us far beyond our planet, far beyond even the familiar stars that appear in the night sky. We'll be exploring one of the quietest and most remarkable phenomena in astronomy, something called a pulsar. It may sound like a complicated word, but the idea behind it begins very simply. Somewhere in the vast darkness of the Milky Way galaxy, there are tiny, collapsed stars turning slowly through space. With each rotation, they send narrow beams of energy sweeping outward into the galaxy. If one of those beams happens to pass across Earth, our telescopes detect a small, repeating signal. A pulse, and then another, and another. Sometimes these pulses arrive once every second. Sometimes dozens of times each second. And in some extraordinary cases, hundreds of times every second, with astonishing regularity. So regular, in fact, that some of these distant stars behave like the most precise clocks in the universe. But before we get there, we'll move slowly through the story of how these objects form, how they spin, and why their quiet signals have helped scientists understand some of the strangest physics known. There's nothing you need to remember tonight. You can simply listen loosely, letting the ideas drift past like distant lights in the sky. If your attention wanders, that's perfectly fine. The story will continue gently, either way. And if you enjoy calm explorations like this, you're always welcome to subscribe or return for more quiet science stories in the future. For now, you can simply settle in, and we'll begin with something that may sound obvious at first. The sky above us often appears silent, but in reality, it is full of signals. The sky is not silent. When we look up at the night sky, the stars usually seem calm and steady. They appear as small points of light scattered across the darkness, distant and quiet. For thousands of years, people could only observe the sky with their eyes, and from that perspective, the stars appeared almost perfectly still. They rose, they crossed the sky, and they set again, night after night, year after year. But once scientists began building radio telescopes in the 20th century, something surprising happened. The sky became noisier, not in the sense of sound. Of course, space remains almost perfectly silent, but in terms of energy signals arriving from distant places, the universe suddenly revealed a hidden conversation that had always been there. Radio telescopes are designed to detect radio waves, a form of electromagnetic radiation that our eyes cannot see. These waves travel through space just like visible light, but they carry information from sources that may otherwise remain invisible. When astronomers pointed these instruments toward the sky, they began detecting faint patterns arriving from all directions. Some came from distant galaxies. Some came from clouds of gas drifting through interstellar space. Some came from energetic regions around black holes. And occasionally, something even more curious appeared. a signal that repeated again and again and again. At first glance, these repeating signals did not resemble anything familiar. Most natural processes in space are messy and irregular. Explosions, turbulence, shifting clouds of gas. They rarely produce patterns that repeat with perfect timing. Yet here were signals arriving with remarkable precision. A brief flash of energy, then darkness, then another flash, and another, each separated by the exact same interval of time. To the instruments listening quietly on Earth, these signals resembled something almost mechanical, as if a distant lighthouse somewhere in the galaxy were sweeping its beam through space. But at the time, no one yet knew what could possibly produce such a rhythm. The pattern itself was the only clue, and it was so precise that it made astronomers pause and wonder, because nature usually does not behave like a perfectly ticking clock. Yet somewhere in the depths of the galaxy, something clearly was. For a moment, scientists simply listened. They recorded the signals, studied their timing, and carefully checked their instruments to make sure nothing on Earth was creating the pattern. But the signals kept returning, steady, patient, unmistakably real. And that alone was quietly astonishing. It's easy to imagine the night sky as empty space between distant stars. But discoveries like this remind us that the universe is filled with processes we cannot see directly. Invisible beams of energy cross the galaxy every moment. Particles stream through interstellar space. Magnetic fields twist and curve around collapsed stars. And occasionally, a distant object sends out a rhythm so steady that it travels across thousands of light years before gently touching the detectors on Earth. A quiet pulse, then another, then another. The sky, it turns out, is not silent at all. It simply speaks in signals we only recently learned how to hear. And one of the most remarkable of those signals would soon lead astronomers to the discovery of an entirely new kind of star. A star that had already lived a full life, collapsed into something far smaller, and yet continued to turn slowly in the darkness, sending its narrow beams across the galaxy like a lighthouse sweeping through an endless cosmic ocean. And that discovery began with a signal that refused to stop returning, which is where our story continues next. A signal that kept returning. In the late 1960s, radio astronomy was still a relatively young science. Large radio dishes had begun listening carefully to the sky, capturing faint patterns of radio waves arriving from far beyond our solar system. Most of the signals they detected were irregular. Gentle static from distant galaxies, drifting emissions from clouds of gas, or brief bursts from energetic cosmic events. But one signal stood out. It arrived with unusual precision, every 1.3 seconds. The telescope detected a brief pulse of radio energy, then silence, then another pulse, arriving exactly when it should, and then another, night after night. The signal continued. It did not drift. It did not fade. It did not behave like random noise or chaotic astrophysical activity. Instead, it behaved like a metronome, steady, patient, and almost impossibly consistent. The signal had first been noticed by a young graduate student named Jocelyn Bell, who was studying long strips of radio telescope recordings at the University of Cambridge. At the time, the data came out not as digital images, but as long paper charts covered in lines and patterns. Most of the lines looked like soft background noise, but occasionally, a tiny section of the chart showed something different, a small, repeating spike. At first, it appeared as a strange little mark in the data, so subtle it might have been easy to overlook. But Bell noticed that the same pattern kept appearing in the same part of the sky. When she examined the recordings more carefully, she realized that the pulses were spaced with extraordinary regularity, exactly 1.3 seconds apart. For scientists studying the messy behavior of cosmic objects, this level of precision was deeply surprising. Stars flare, explode, flicker, and shift. Gas clouds swirl unpredictably. Black holes devour matter in chaotic bursts. But this signal behaved like a perfectly timed clock. It's easy to miss how strange that really is. Across the vastness of the galaxy, something was sending out a signal every 1.3 seconds. Not almost every 1.3 seconds. Not approximately every 1.3 seconds. But almost exactly on schedule. The first task, of course, was to rule out anything happening on Earth. Radio telescopes can sometimes detect interference from aircraft, electrical equipment, or communication signals. But this signal moved across the sky exactly the way a distant astronomical source should. As the Earth rotated, the signal appeared and disappeared at the right times, just like a star would. That meant it was coming from space, and that left astronomers with a puzzle. What kind of natural object could produce such a perfectly repeating signal? For a brief moment, and only very briefly, a few researchers even wondered whether the pattern might be artificial. The idea of an intelligent civilization sending signals through space had long been part of scientific speculation. And this signal, with its precise rhythm, did resemble the kind of repeating pattern humans might design. But scientists are cautious about such possibilities, and they quickly began searching for more ordinary explanations. Soon enough, they found something even more fascinating. The signal wasn't unique. As radio telescopes continued scanning the sky, they began discovering other repeating signals coming from different parts of the galaxy. Each one had its own rhythm. Some pulsed every second, others every few seconds. Some even pulsed dozens of times per second. Clearly, this was not a single mysterious transmitter. It was a new category of astronomical object, something that had existed quietly in the universe all along, waiting for instruments sensitive enough to notice its rhythm. The signals were given a simple name, pulses, and the objects producing them became known as pulsars. But identifying the signals was only the beginning. The deeper question remained, what exactly was a pulsar? Because whatever it was, it had to satisfy a remarkable set of conditions. It had to produce beams of energy powerful enough to travel across thousands of light years. It had to rotate or repeat with astonishing precision. And it had to do all of this while remaining stable for years. Perhaps even millions of years. At first glance, no ordinary star could behave this way. The stars we see in the night sky are enormous spheres of glowing gas, many times larger than Earth. They burn through nuclear fuel in their cores, producing energy that flows outward as light and heat. But these stars rotate slowly. Some take days or weeks to complete a single turn. None could spin fast enough to produce pulses every second. So, whatever pulsars were, they had to be something much smaller, much denser, and far stranger than the stars people had been observing for centuries. The answer, as astronomers soon realized, lay in the life cycle of massive stars, because not every star ends its life quietly. Some of them collapse into objects so extreme that they compress the mass of a star into a sphere barely larger than a city. And when that happens, something remarkable occurs. The star begins to spin faster and faster until it becomes one of the most extraordinary objects in the universe, a neutron star. And under the right conditions, that neutron star becomes a pulsar, a rotating beacon sending its quiet signals across the galaxy. To understand how this transformation happens, we have to step back much earlier in the story of a star's life, long before the pulses begin, long before the collapse, back to a time when the star itself still shines normally, balanced between gravity pulling inward and nuclear energy pushing outward. For most of its life, a star exists in that delicate balance. But eventually, that balance changes. And when it does, the star's story takes a very different turn. The first pulsar, when astronomers finally understood what those repeating signals represented, the discovery quietly reshaped how scientists thought about the universe. The mysterious pulses were not messages. They were not machines. They were not signals sent intentionally across space. Instead, they were the natural rhythm of a star that had already lived, died, and collapsed into something entirely new. The object producing the pulses was a neutron star, and because of the way it spun and emitted radiation, it became known as a pulsar. To imagine this kind of star, it helps to begin with something familiar. Most of the stars we see in the night sky are enormous spheres of glowing gas. Our own sun, for example, is about 1.4 million kilometers across. Inside that vast sphere, nuclear reactions fuse hydrogen atoms together, releasing the energy that shines outward as sunlight. For most of a star's life, this process keeps everything in balance. Gravity constantly pulls the star inward, trying to collapse it. At the same time, the intense heat and pressure produced by nuclear fusion push outward. The two forces hold each other in a quiet agreement. The star remains stable, shining steadily for millions or billions of years. But for very massive stars, that balance eventually breaks. When the fuel inside the core is exhausted, the outward pressure begins to fade. Gravity, which has been waiting patiently the entire time, starts to win. The core begins to collapse. At first, the collapse happens quickly, faster than anything we normally imagine happening inside a star. Matter falls inward, squeezed by gravity with extraordinary force. Electrons and protons, the familiar building blocks of atoms, are pushed together so tightly that they merge into neutrons, and the structure of ordinary matter begins to disappear. The star's core compresses into something entirely different, a neutron star, and the scale of that transformation is difficult to picture. Imagine taking a star with roughly the mass of our sun and compressing it into a sphere only about 20 kilometers across. That distance is small enough to drive across in less than half an hour. Yet inside that small region lies more mass than an entire star once contained. The density becomes almost beyond ordinary intuition. A teaspoon of neutron star material would weigh billions of tons. Matter at this scale behaves in ways that scientists are still trying to fully understand. Atoms no longer exist in their usual form. The interior becomes a dense sea of neutrons packed tightly together, forming one of the most extreme environments known anywhere in the universe. But the strange story of neutron stars does not end with their density. Another important property appears as well: rotation. Before the collapse, the original star was already turning slowly in space. Most stars rotate, though the motion is usually gentle and difficult to notice from a distance. But when the star collapses, something subtle yet powerful happens. The same rotation becomes concentrated into a much smaller space. This is a principle known as conservation of angular momentum. You may have seen a simple demonstration of it in everyday life. If a figure skater spins with their arms extended, their rotation is relatively slow. But when they pull their arms inward toward their body, their spin becomes faster. The same physical rule applies to collapsing stars. As the star's core shrinks from hundreds of thousands of kilometers across to only 20 kilometers, its rotation speeds up dramatically. What was once a slow turn can become dozens of rotations each second. In some cases, even hundreds. A neutron star can spin with extraordinary speed, and if that star also has strong magnetic fields, which most neutron stars do, the result becomes something truly remarkable. The spinning star begins to send beams of radiation out into space. These beams do not shine evenly in all directions like ordinary starlight. Instead, they emerge from the star's magnetic poles, forming narrow streams of energy that extend outward into the surrounding darkness. Because the star is rotating, these beams sweep through space as it turns, and if one of those beams crosses the Earth, astronomers detect a brief flash of radiation, a pulse. Then the star rotates again. Another pulse, and another. The signal arrives each time the beam points toward us. From Earth, the effect resembles the beam of a lighthouse sweeping across the horizon. The lighthouse itself never turns on and off. Its light shines continuously. But as the beam rotates, observers see a brief flash each time it passes their direction. A pulsar works in almost exactly the same way, except instead of shining across an ocean, its beams travel across the vast emptiness of interstellar space. Each rotation sends another pulse outward. Some of these pulses repeat every second, some every fraction of a second, some even faster. And despite the incredible forces involved, gravity, magnetism, radiation, the timing of these pulses can remain astonishingly precise. For years, for decades, sometimes even longer, it may seem like the kind of thing we should already know. And yet, the discovery of pulsars revealed just how strange the universe can be. A star collapses. Its matter compresses beyond ordinary experience. Its rotation accelerates, and instead of fading away, the remnant becomes a quiet, rotating beacon, sending signals across the galaxy. And those signals, traveling patiently through space, eventually arrive here, touching the detectors of radio telescopes on Earth. A faint pulse, then another, and another, each one marking the steady turning of a collapsed star somewhere far away in the dark. The life of massive stars. To understand why pulsars exist at all, it helps to step even further back in time. Long before the pulses, long before the collapse, back to the long and steady life of an ordinary massive star. At first glance, stars seem almost timeless. They rise each night, shine with quiet steadiness, and appear unchanged across generations. The same stars seen by ancient civilizations still shine in our skies today, but from the inside, stars are never truly still. Deep within their cores, immense processes unfold continuously. Temperatures climb to millions of degrees, pressures become extraordinary, and matter itself transforms. The heart of a star is a place where atoms fuse together. In stars like our sun, hydrogen atoms combine to form helium. This process releases enormous amounts of energy, which flows outward through the star's layers and eventually escapes as light and heat. That energy is what keeps a star shining. But it also plays another role that is less obvious. It keeps the star from collapsing. Gravity is always pulling the star inward, drawing all of its mass toward the center. If gravity were the only force at work, the star would quickly collapse into a much smaller object. But the energy produced by nuclear fusion pushes outward at the same time. The two forces balance each other. Gravity pulls inward, energy pushes outward, and the star remains stable. For most of a star's life, this balance is remarkably steady. The star shines for millions, sometimes billions, of years without dramatic change. Yet, even during this long, quiet period, the star is slowly evolving. As hydrogen fuel in the core is consumed, the star begins fusing heavier elements. Helium forms carbon. Carbon forms oxygen. In the most massive stars, the chain of fusion continues, building increasingly heavier elements deep inside the stellar core. Each stage releases energy, maintaining the outward pressure that keeps gravity in check. But this process cannot continue forever. There is a limit to how far nuclear fusion can go. Eventually, the star begins producing iron in its core. And iron is different from the lighter elements that came before it. Fusing iron does not release energy. Instead, it consumes energy. This changes everything. For millions of years, fusion has been the star's internal engine, the force that holds gravity back. But when iron accumulates in the core, that engine begins to fail. Energy production slows, the outward pressure weakens, and gravity, which has been waiting patiently all along, finally begins to dominate. At first, the change is subtle. The core contracts slightly. Temperatures rise even further. New reactions briefly occur, but soon the situation becomes unstable. Without enough outward pressure, the core can no longer support the enormous weight of the star's outer layers. Gravity begins pulling everything inward with increasing speed. The collapse begins, and it happens astonishingly fast. A core that once balanced gravity for millions of years can collapse in less than a second. Matter rushes inward under the star's own weight. The atoms themselves begin to change as the pressure climbs higher and higher. Electrons and protons, particles that normally remain separate inside atoms, are pushed together. They combine, and in doing so, they form neutrons. The familiar structure of atoms disappears. What remains is something far denser. A new kind of matter begins to form. Matter composed almost entirely of neutrons packed tightly together. The core has become a neutron star, but the collapse of the core does something else as well. It triggers one of the most dramatic events in the universe, because as the core suddenly compresses into this dense sphere, the outer layers of the star are still rushing inward. When they strike the newly formed neutron core, the material rebounds outward with tremendous force. The star explodes. This explosion is called a supernova. For a brief time, the dying star can shine brighter than entire galaxies. The expanding cloud of gas and debris spreads outward through space, carrying newly formed elements with it. Iron, oxygen, carbon, and many other elements forged inside the star are scattered across the galaxy over immense stretches of time. Some of this material will eventually become part of new stars, new planets, and perhaps even living organisms. But at the center of that expanding cloud, something small and dense remains. The neutron star, only about 20 kilometers across, yet containing the mass of an entire star. At first, it might seem like this should be the end of the story. The star has collapsed. The explosion has passed. The debris is drifting outward into space. But inside that tiny remnant, something extraordinary continues. The star is spinning, and because of the enormous compression that created it, the rotation has become incredibly fast. The neutron star turns again, and again, and again, each rotation sweeping its powerful magnetic beams across the darkness of space. And when one of those beams crosses Earth, we detect it as a pulse, a quiet signal traveling across the galaxy, the steady rhythm of a collapsed star that is still turning in the dark, the end of the balance. For most of its life, a massive star exists in that quiet balance between gravity and energy. Gravity is always pulling inward, trying to compress the star. At the same time, the heat and radiation created by nuclear fusion push outward from the core. These two forces hold each other in place, and the star shines steadily for millions of years. From the outside, this balance looks calm and unchanging, but inside the star, the situation is always slowly evolving. Every moment, hydrogen atoms fuse into helium. Over long stretches of time, helium begins to fuse into heavier elements. In very massive stars, the chain continues further, building layers of increasingly complex elements deep inside the star's interior. If we could somehow look inside such a star near the end of its life, we might see something that resembles the layers of an onion. Near the center lies the heaviest material, iron. Around that core are shells where lighter elements are still fusing. Silicon, oxygen, carbon, helium, and hydrogen farther out. Each shell continues producing energy, and for a while, the star still shines as it always has. But the presence of iron in the center signals that the star is approaching a turning point. Iron is a strange element in the life cycle of stars. Most fusion reactions release energy. When hydrogen fuses into helium energy flows outward. When helium fuses into carbon, more energy is released. These reactions help hold the star up against gravity. But iron behaves differently. When iron atoms fuse together, the reaction does not release energy. Instead, it requires energy to occur. So, when the core of a massive star becomes mostly iron, the internal engine that has supported the star for millions of years begins to fail. The outward push weakens. Gravity, which has been waiting patiently all this time, begins to take control. At first, the core contracts only slightly. Temperatures rise further as gravity compresses the material. New reactions briefly ignite in the surrounding layers, but the core itself can no longer generate enough energy to hold up the star's enormous mass. The collapse begins quietly, then it accelerates. Gravity pulls the core inward, faster and faster. Matter falls toward the center at incredible speeds. The pressure becomes so intense that the normal structure of atoms begins to break down. Electrons, which usually orbit atomic nuclei, are forced directly into the nuclei themselves. When electrons combine with protons, they form neutrons. This process happens throughout the collapsing core. Atoms disappear. What remains is a dense sea of neutrons pressed tightly together by gravity. Within less than a second, the core shrinks from a region thousands of kilometers across to something only about 20 kilometers wide. It is difficult to imagine such a transformation. A structure that once filled a vast stellar interior suddenly compresses into a sphere smaller than a city, and the collapse does not happen gently. The outer layers of the star are still rushing inward when they strike the newly formed neutron core. That core is so dense that it resists further compression, and the infalling material rebounds outward. A powerful shock wave forms. The shock wave travels outward through the star's layers, carrying enormous energy with it, and the star explodes. For a brief time, the supernova becomes one of the brightest events in the universe. The expanding cloud of gas glows across space, spreading the star's material into the surrounding galaxy. The debris travels outward for thousands of years, forming vast glowing nebulae that astronomers can observe long after the explosion itself has faded. But at the center of that expanding cloud, something very small remains. The neutron star, only about 20 kilometers across, yet containing roughly the same mass as the Sun. Its gravity is extraordinary. If you stood near its surface, which of course would be impossible, gravity would be billions of times stronger than what we experience on Earth. Matter there behaves in ways that scientists are still studying. But one thing about this remnant is immediately clear. It is spinning. Before the collapse, the original star rotated slowly in space, perhaps taking days or weeks to complete a single turn. But when the star collapsed, its size shrank enormously, while its rotational momentum remained. Just like the spinning skater who pulls their arms inward and begins turning faster, the neutron star's rotation accelerates dramatically. What was once a slow stellar turn becomes a rapid spin. Many neutron stars rotate several times every second. Some rotate dozens of times each second. And under the right conditions, these rapidly spinning neutron stars become pulsars. Their magnetic fields guide streams of charged particles into narrow beams that extend outward into space. As the star rotates, those beams sweep through the darkness of the galaxy, and every time one of those beams passes across Earth, we detect a pulse, a brief signal, then silence, then another signal, over and over again. The quiet rhythm of a collapsed star still turning in the dark. A city-sized star. When people first hear about neutron stars, the most surprising detail is usually their size, or rather, their lack of it. The star that produced the supernova may once have been enormous, millions of kilometers across, shining brilliantly for millions of years. But after the collapse, the remnant left behind is astonishingly small. Most neutron stars measure only about 20 kilometers from one side to the other. That is roughly the distance across a large city. And yet, inside that small sphere lies almost the entire mass of the original stellar core. In many cases, that mass is comparable to our sun. It's easy to say those numbers out loud, but the mind has trouble holding the image together. We are used to thinking of stars as enormous glowing spheres, vast, diffuse, and luminous. A neutron star is something different. It is a star compressed to an extreme degree. If you could somehow scoop up a teaspoon of material from its surface, that tiny amount of matter would weigh billions of tons on Earth. The density is almost beyond ordinary imagination. Matter there is packed together so tightly that the familiar structure of atoms has disappeared. Electrons no longer orbit around nuclei the way they do in ordinary matter. Instead, most of the particles have merged into neutrons, creating a dense, tightly packed interior that behaves very differently from the materials we encounter in everyday life. Scientists sometimes describe the interior of a neutron star as a kind of quantum fluid, a sea of particles moving together under enormous pressure. Even the outer surface of the star is unusual. The crust of a neutron star is thought to be incredibly rigid, perhaps the strongest material structure that exists anywhere in the universe. Beneath it lies layers of matter so dense that their exact behavior remains one of the great puzzles of modern physics. From inside the system, it's hard to see the whole shape of what is happening, but astronomers study neutron stars precisely because they allow us to explore physics under conditions impossible to reproduce on Earth. Inside laboratories, scientists can generate intense temperatures or pressures for brief moments. But the interior of a neutron star contains pressures and densities that remain stable for millions of years. In that sense, these small stellar remnants become natural laboratories, places where gravity compresses matter to its limits and reveals behaviors we would otherwise never see. And yet, despite all this extraordinary density, neutron stars are not motionless. They rotate. The collapse that formed them dramatically increased their rotational speed. As the original star shrank, the same angular momentum became concentrated into a far smaller object. The result is motion that can be astonishingly fast. Many neutron stars spin several times every second. Some spin dozens of times per second. And in certain rare cases, a neutron star may rotate hundreds of times each second. That means the surface of the star is moving through space at extraordinary speeds. Yet the star itself remains remarkably stable. It is easy to imagine that such a rapidly spinning object might tear itself apart. But gravity at the surface of a neutron star is so powerful that it holds everything tightly in place. Matter there is bound together by forces far stronger than anything we experience on Earth. So the star continues to turn, again and again and again. This steady rotation becomes the key to the strange signals astronomers detect from pulsars, because as the neutron star spins, another invisible feature comes into play: its magnetic field. And neutron stars possess magnetic fields so powerful that they reshape the space around them in dramatic ways. Invisible lines of magnetic force extend outward from the star's surface, guiding streams of charged particles into narrow channels. These particles accelerate along the magnetic poles of the star, producing intense beams of radiation that shoot outward into space. But there is an important detail that makes pulsars possible. The magnetic poles of a neutron star are usually not aligned with its rotation. In other words, the direction the magnetic field points is slightly tilted relative to the way the star spins. And that small tilt changes everything, because as the neutron star rotates, its magnetic poles sweep through space. The beams of radiation attached to those poles sweep outward like rotating flashlights. Most of the time, those beams travel through empty space without encountering anything at all. But occasionally, one of them crosses our direction. When that happens, telescopes on Earth detect a brief pulse of energy. Then the star rotates again. The beam passes our direction again. Another pulse. From our perspective, it appears as though the star is blinking on and off. But the star itself is not flickering. It is simply rotating, and we are standing in the path of its sweeping beam, a quiet lighthouse turning slowly through the dark ocean of the galaxy, each pulse marking another rotation of a collapsed star only 20 kilometers wide, yet carrying the mass of an entire sun. And that rotation, guided by invisible magnetic forces, becomes one of the most reliable rhythms anywhere in the universe. A rhythm that continues whether anyone is listening or not, turning patiently through the darkness of space. The spin of collapse. One of the most remarkable things about pulsars is not just how dense they are, but how quickly they rotate. The rotation begins long before the pulsar exists. Almost every star in the universe spins, at least a little. Stars form from slowly rotating clouds of gas and dust, and as those clouds collapse to form new stars, a small amount of that rotation remains. In ordinary stars, the motion is usually gentle. A star like our sun rotates once roughly every 25 days at its equator. Larger stars can rotate somewhat faster, but even then, the motion unfolds slowly on human timescales. But when a massive star collapses into a neutron star, something very different happens. The collapse compresses the star's core enormously. A region that once measured thousands of kilometers across shrinks down to a sphere barely 20 kilometers wide. And yet, the original rotation does not disappear. Instead, the same rotational momentum becomes concentrated into that much smaller space. This is a basic physical principle called the conservation of angular momentum. It appears throughout the universe, from spinning galaxies to small motions we can observe here on Earth. You may have seen a familiar demonstration of this principle in ice skating. A figure skater spinning with their arms extended, rotate slowly at first, but when they draw their arms inward toward their body, their spin becomes noticeably faster. Nothing external is pushing them to spin faster. Instead, the same rotational motion is simply concentrated into a smaller shape. The collapsing core of a star behaves in a similar way. As the star shrinks, its rotation accelerates. What was once a slow stellar turn becomes something far more rapid. A neutron star can complete an entire rotation in just a fraction of a second. Many spin several times each second. Some rotate dozens of times every second, and in certain extraordinary cases, neutron stars spin hundreds of times each second. It's easy to miss how unusual that really is. Imagine a sphere, roughly the size of a city, spinning several hundred times every second. The surface of the star moves through space at tremendous speeds, yet the structure holds together under the powerful grip of gravity. The gravity on a neutron star is so intense that even such rapid motion cannot tear it apart. In fact, gravity helps maintain the star's stability. The material of the star is held tightly in place, compressed by forces far beyond anything we experience on Earth. This means the neutron star can continue rotating for extraordinarily long periods of time. Years, thousands of years, even millions of years. But the rotation alone does not produce the pulses astronomers observe. For that, another ingredient is needed: magnetism. Neutron stars possess some of the most powerful magnetic fields known anywhere in the universe. When the star collapses, its magnetic field is compressed along with the rest of the star's material. The result is a magnetic environment of astonishing strength. These magnetic fields extend outward from the star into space, forming invisible lines of force that guide charged particles moving near the surface. Electrons and other particles become trapped along these magnetic paths, accelerating as they move. As they accelerate, they emit radiation. This radiation flows outward along the magnetic poles of the star in narrow beams. And here again, something subtle becomes important. The magnetic poles of the star are usually tilted relative to the star's rotation, so the beams do not point straight outward in a fixed direction. Instead, they sweep through space as the star rotates. If the beam never crosses Earth, we may never know the pulsar exists. But if our planet happens to lie in the path of the sweeping beam, telescopes detect a flash each time the beam passes, a pulse. Then the beam rotates away. Darkness again. Then another pulse when the beam returns. From our perspective, it looks as though the star itself is turning on and off. But the star is actually shining continuously along those narrow magnetic channels. It is our position relative to the beam that creates the rhythm we observe, and that rhythm can be extraordinarily precise. Some pulsars rotate so steadily that their pulses arrive with a regularity comparable to the most advanced clocks built by humans. Across thousands of light years of empty space, a collapsed star continues to turn, sending out its beams again and again. The motion is patient, reliable, quietly consistent. It may seem like the kind of thing we should already know. And yet, the discovery of pulsars revealed that the universe contains objects whose precision rivals our own technology. A star, long after its explosive death, becoming a kind of natural timekeeper, each rotation marking another moment in the vast, slow passage of cosmic time. And that steady rhythm continues, whether anyone notices it or not, somewhere in the galaxy. Even now, countless neutron stars are spinning through the darkness, their invisible beams sweeping across space with quiet, unwavering regularity. Magnetic giants. Rotation alone does not make a pulsar. A neutron star could spin very quickly and still remain invisible to us if nothing about it produced a beam of radiation directed outward into space. What turns a spinning neutron star into a pulsar is something less visible, but just as powerful. Its magnetic field. Magnetism exists everywhere in the universe. Our own planet has a magnetic field that gently guides compass needles and shields Earth from streams of charged particles flowing outward from the sun. The sun itself has a magnetic field as well. In fact, the sun's magnetism shapes many of the phenomena we see in solar activity. Sunspots, solar flares, and the streams of particles that form the solar wind. But the magnetic field of a neutron star is something entirely different in scale. When the original star collapsed to form the neutron star, the magnetic field it carried was compressed along with everything else. Just as the star's matter was squeezed into a tiny sphere, its magnetic field lines were squeezed inward too. And when magnetic fields are compressed like that, they grow enormously stronger. The result is a magnetic field that can be trillions of times stronger than the one surrounding Earth. It's difficult to imagine what such a field would feel like. In the environment near a neutron star, magnetism becomes one of the dominant forces shaping how matter behaves. Charged particles, electrons, and other tiny pieces of matter cannot move freely there. Instead, they are guided tightly along invisible magnetic pathways. These pathways extend outward from the neutron star into space, forming large looping structures that resemble the magnetic patterns around ordinary stars, but vastly more intense. Near the star's magnetic poles, these lines of force open outward, allowing streams of particles to escape along them. As these particles accelerate along the magnetic field, something interesting happens. Accelerating charged particles emit radiation. The process occurs everywhere in physics. Whenever electrons are forced to change direction or speed, they release energy in the form of electromagnetic waves. Around a neutron star, this process becomes extremely powerful. Electrons spiral along magnetic field lines at enormous speeds. As they do, they emit radiation across a wide range of wavelengths. Radio waves, X-rays, and sometimes even gamma rays. The radiation does not spread evenly in all directions. Instead, it becomes concentrated into narrow beams emerging from the magnetic poles of the neutron star. These beams extend far out into space. If we could see them directly, they might look like two long cones of light projecting from opposite sides of the star. But there is one more detail that makes pulsars possible. The magnetic poles of a neutron star are rarely aligned perfectly with the star's rotation. In other words, the direction of the magnetic field is slightly tilted compared to the axis around which the star spins. That tilt means the beams of radiation do not remain fixed in space. Instead, they sweep outward as the star rotates. Imagine a rotating flashlight whose beam points slightly to the side rather than straight ahead. As the flashlight spins, the beam traces a circular path through the darkness. A neutron star behaves in much the same way. With every rotation, its beams sweep across the surrounding space. Most of the time, Those beams pass through empty regions of the galaxy, but occasionally, one of them crosses the direction of Earth, and when it does, our telescopes briefly detect the radiation. A flash, then the beam rotates away again. The star itself has not turned off. The radiation continues streaming outward along its magnetic poles. We simply move in and out of the beam as the star spins. This is why the signal appears as a repeating pulse. Each pulse marks a single rotation of the neutron star, and the remarkable thing is how steady those rotations can be. Some pulsars maintain their rhythm with astonishing reliability. Their pulses arrive with such precision that astronomers can measure tiny changes in timing, shifts smaller than a millionth of a second, across thousands of light years of empty space. The star keeps turning, again and again and again, each rotation sending its beams across the galaxy. It's easy to miss how strange that really is. A star that has already exploded and collapsed into a tiny sphere continues to act like a rotating beacon. Its magnetic field channels streams of particles. Those particles emit radiation, and that radiation travels through the darkness of space until, occasionally, it brushes past a small blue planet orbiting an ordinary star. For a brief moment, a telescope detects the signal. A pulse, then silence, then another pulse when the beam returns, and the rhythm continues, patient and unwavering, as the neutron star keeps turning quietly in the dark. Beams from the poles. Once a neutron star begins spinning with its powerful magnetic field, something subtle and beautiful happens in the space around it. The magnetic field does not simply sit there like an invisible shell. Instead, it forms a complex structure of lines of force stretching far beyond the surface of the star. These lines guide the motion of charged particles, tiny pieces of matter such as electrons, that move through the star's surrounding environment near the star's surface. Gravity is immensely strong, and the magnetic field is even stronger. Together, they create a region where particles are constantly being accelerated and redirected. Charged particles follow the magnetic field lines almost like trains following invisible rails. They spiral along those lines, gaining speed as they move. And whenever charged particles accelerate in this way, they emit energy. In the environment of a neutron star, this process produces intense radiation. The radiation can appear in several forms: radio waves, which radio telescopes detect most easily, as well as X-rays, and sometimes even higher energy gamma rays. These emissions do not spread out evenly like the soft glow of a normal star. Instead, the radiation becomes concentrated into narrow beams that emerge from the star's magnetic poles. If you could somehow watch this from nearby, safely and from a great distance, you might see two cones of radiation streaming outward from opposite sides of the neutron star. The beams extend far into space, like enormous searchlights shining across the darkness. But there is a small misalignment that gives pulsars their distinctive rhythm. The axis around which the neutron star spins is not perfectly aligned with the direction of its magnetic poles. The star spins around one line. The magnetic beams point along another. That difference means the beams move through space as the star rotates. Each time the neutron star completes a rotation, its beams sweep across a wide circular path in the surrounding darkness. Most of the time, Those beams pass through empty space where no observer is present. But occasionally, one of those sweeping beams crosses Earth, and when it does, our instruments detect the radiation as a sudden pulse, a brief signal. Then the beam continues past us and disappears again. From our perspective, the star appears to blink, but the star itself is not turning on and off. The beams are always shining outward from the magnetic poles. The pulses we observe simply occur when the sweeping beam briefly crosses our direction. This is why astronomers often compare pulsars to lighthouses. A lighthouse sends a beam of light rotating across the ocean. A ship far away sees a flash each time the beam sweeps past. Between flashes, the light is still shining. It is simply pointing somewhere else. Pulsars behave in much the same way, except the beams are not lighting up waves on the ocean. They are crossing the vast emptiness of interstellar space, and the lighthouse itself is not a tower on a coastline. It is a collapsed star, only 20 kilometers across, spinning in the darkness of the galaxy. Each pulse that reaches Earth marks one full rotation of that star. Some pulsars rotate once every second, others rotate several times each second, and some, known as millisecond pulsars, rotate hundreds of times every second. Imagine that for a moment. A star containing more mass than the sun, compressed into the size of a city, spinning hundreds of times each second while sending beams of radiation across the galaxy. Yet, despite this incredible motion, many pulsars remain astonishingly stable. The pulses they produce arrive with extraordinary regularity. Astronomers can predict their timing with remarkable accuracy, sometimes measuring changes smaller than a millionth of a second. Across distances of thousands of light years, these rotating stars maintain their quiet rhythm, again and again and again. Even the most dramatic changes often come from small adjustments. In this case, the small tilt between a neutron star's magnetic field and its rotation creates one of the most recognizable signals in astronomy, a repeating pulse traveling patiently through space, a pulse that began its journey perhaps centuries ago, long before the invention of radio telescopes, before the first satellites orbited Earth, before anyone knew that such stars even existed. And now, quietly, those pulses arrive, touching the sensitive instruments of telescopes pointed toward the sky, each one marking another turn of a distant neutron star, still spinning, still sending its beams across the dark ocean of the galaxy. The lighthouse effect. When astronomers first began studying pulsars, one of the most helpful ways to imagine their behavior was through a simple image. A lighthouse. Along many coastlines, a lighthouse sends a rotating beam of light across the dark surface of the ocean. The light itself shines continuously, but because the beam turns slowly, a ship at sea only sees the light briefly each time it sweeps past. A flash, then darkness, then another flash when the beam returns. The lighthouse itself never blinks. It simply rotates. Pulsars work in much the same way. A neutron star emits narrow beams of radiation along its magnetic poles. Those beams are always present, streaming outward into space. But because the star is spinning, the beams sweep across the galaxy like long searchlights turning through the dark. Most of the time, those beams travel through empty space, But if Earth happens to lie along the path of one of those sweeping beams, telescopes detect a brief signal each time the beam crosses our direction. A pulse. Then the beam rotates away again. From Earth, the star appears to turn on and off. But that is only an illusion created by the rotation. The pulses are simply the moments when the beam points toward us. Each one marks a single turn of the neutron star, and this rhythm can be remarkably steady. Some pulsars rotate once every second, producing a pulse each second like the ticking of a distant clock. Others rotate several times per second, creating pulses that arrive faster than the beat of a human heart. And then there are the millisecond pulsars. These objects spin so quickly that their pulses arrive only thousandths of a second apart. A single neutron star can complete hundreds of rotations in the time it takes to blink. It may seem almost impossible for a star to spin so rapidly without breaking apart, but neutron stars are held together by gravity so powerful that even such extreme motion cannot tear them apart. The matter inside them is compressed into one of the densest forms known, and the star behaves almost like a perfectly balanced spinning object. The rotation remains stable, reliable, predictable, and that reliability is one of the most surprising features of pulsars. Astronomers have measured the timing of pulsar pulses for decades. Some pulsars behave so consistently that their signals rival the accuracy of atomic clocks. The devices scientists use to define the most precise measurements of time, across distances of thousands of light years, a pulsar can keep time with astonishing precision. Every rotation produces another pulse. Every pulse arrives almost exactly when it should. It is easy to miss how strange that really is. Inside one of the most extreme environments in the universe, a collapsed star with crushing gravity and enormous magnetic forces, the motion remains orderly, calm, steady, a quiet cosmic rhythm continuing for years, centuries, even millions of years. This precision allows astronomers to do something remarkable. By carefully measuring the arrival time of pulses from a pulsar, scientists can detect incredibly tiny changes in motion and gravity. The pulsar becomes a kind of natural clock placed somewhere deep in the galaxy. If something slightly alters the distance between the pulsar and Earth, perhaps a shift in gravitational fields or a tiny movement of space itself, the timing of the pulses changes by a small amount, and that change can be measured. In this way, pulsars help astronomers study phenomena that would otherwise remain invisible. Ripples in spacetime, the motion of stars within the Milky Way, the gravitational influence of massive objects, all revealed through the quiet rhythm of a spinning neutron star. It is an elegant reminder that the universe often hides its most powerful tools inside the smallest objects. A star that once ended its life in a supernova explosion becomes something new, a dense, rotating remnant, a lighthouse in the galaxy, its beams sweeping outward across the darkness, touching distant worlds with brief signals of energy. A pulse, then another, each one marking another turn of a star, only 20 kilometers wide, yet powerful enough to send its rhythm across thousands of light years of space. And somewhere, even now, countless pulsars continue their patient rotation, their beams moving quietly through the dark, whether anyone is listening or not, faster than expected. When the first pulsars were discovered, their repeating signals were already surprising. A pulse every second was unusual enough But as astronomers began searching more carefully across the sky, they found something even more astonishing. Some pulsars were spinning far faster. Instead of rotating once every second, these neutron stars were completing dozens of rotations each second. And in certain extraordinary cases, the rotation became even more extreme. Hundreds of rotations every second. At first glance, that seems almost impossible. Imagine an object the size of a city spinning hundreds of times each second. Its surface would be moving through space at incredible speed, yet neutron stars are so dense and gravity around them so powerful that this motion remains stable. Nothing flies off. The star simply continues turning, again and again and again. These extremely fast objects became known as millisecond pulsars because the pulses they produce arrive only milliseconds apart. A millisecond is 1,000th of a second. So, instead of waiting an entire second between pulses, astronomers might detect hundreds of pulses in the span of a single second. The signals appear as an almost continuous rhythm in the data, a rapid sequence of ticks from a star far away in the galaxy. What makes this even more remarkable is how steady the rotation can remain, even at such incredible speeds. Many millisecond pulsars maintain extraordinary stability. Their timing is so consistent that scientists can predict the arrival of pulses with remarkable accuracy. In some cases, pulsars rival the precision of atomic clocks on Earth. Atomic clocks measure time by observing the behavior of atoms under carefully controlled conditions. They are among the most precise instruments humans have ever created. Yet far out in the galaxy, a collapsed star, formed in a supernova explosion millions of years ago, can keep time almost as reliably. It may seem like the kind of thing we should already know, and yet the discovery of millisecond pulsars revealed just how diverse neutron stars can be. Some spin slowly, some spin rapidly, and some spin at speeds that stretch the limits of our imagination. But these extraordinary rotation rates also raise an interesting question. How did the star begin spinning that fast? When a neutron star first forms during a supernova collapse, its rotation can indeed accelerate dramatically. The shrinking core concentrates the star's angular momentum, increasing its spin, much like a skater pulling their arms inward. But the fastest pulsars often seem too fast to be explained by collapse alone. Something else must be happening. Astronomers eventually realized that many of the fastest pulsars live in binary systems, pairs of stars orbiting each other closely. In such systems, the neutron star is not alone. Nearby, another star continues to shine. And over time, the powerful gravity of the neutron star begins pulling material from its companion. Gas from the neighboring star drifts toward the neutron star, forming a swirling disk of matter around it. As this material spirals inward, it transfers angular momentum to the neutron star. In simple terms, the gas acts like a gentle push. Little by little, the neutron star spins faster. Over thousands or millions of years, this process can accelerate the star's rotation dramatically. A pulsar that once spun slowly can be recycled, gradually wound up again by the flow of matter from its companion star. Eventually, it becomes a millisecond pulsar, one of the fastest spinning objects in the known universe. Yet despite this incredible speed, the motion remains calm and regular. Each rotation produces another beam sweep. Each beam sweep produces another pulse. Hundreds of pulses each second, traveling outward through space, across distances of thousands of light years. Those pulses carry the quiet rhythm of the spinning star, a rhythm that may continue for millions of years. A star that once exploded, collapsed, and nearly disappeared has become something else entirely. A rotating clock, a distant beacon, a small but powerful signal crossing the vast darkness of the Milky Way. And even now, many of those pulses are already on their way toward Earth, traveling patiently through interstellar space. A pulse that began its journey perhaps centuries ago, another pulse following close behind, each one marking another turn of a tiny star spinning quietly somewhere in the galaxy. Cosmic clocks. One of the quiet surprises of pulsars is not only how fast they spin, but how reliably they continue spinning once that motion has begun. In everyday life, spinning objects usually slow down quickly. A toy top turns for a short time before friction with the surface gradually drains its motion. Wheels eventually lose momentum. Even the Earth's rotation changes slightly over long periods because of tidal forces, but pulsars exist in a very different environment. They rotate in the near-perfect vacuum of space, far from the kinds of friction that slow objects down on Earth. And because the neutron star itself is incredibly dense and rigid, its structure remains extremely stable as it spins. The result is a kind of cosmic clock. Every rotation of the neutron star produces another sweep of its radiation beam, and every sweep produces another pulse when that beam crosses Earth. Pulse, then another pulse, then another. The intervals between these pulses can be measured with astonishing precision. In fact, some pulsars maintain such stable timing that astronomers can predict the arrival of their pulses years into the future with remarkable accuracy. The pattern continues so steadily that even tiny irregularities become noticeable. Imagine listening to the ticking of a clock that has been running continuously for decades. If the clock suddenly lost or gained even a fraction of a second, the change would be obvious. Pulsars allow astronomers to perform a similar kind of measurement on a cosmic scale. Across thousands of light years, the pulses arrive like distant ticks from a rotating star, and when the timing shifts, even slightly, it can reveal something happening in the space between the pulsar and Earth. For example, the motion of the Earth itself affects the arrival times of pulses. As our planet moves around the Sun, the distance between Earth and a pulsar changes slightly. That small difference alters the time it takes for each pulse to reach us. Astronomers can measure these changes carefully, allowing them to determine the position of pulsars in the sky with remarkable precision. But the timing signals can reveal even more subtle effects. Gravity itself can influence the arrival time of pulsar signals. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time around them. When pulses travel through these curved regions, their path and timing can shift slightly. By studying these changes, astronomers have been able to test some of the deepest predictions of modern physics. In fact, pulsars have helped provide important evidence for gravitational waves, tiny ripples in space-time produced by massive objects moving through the universe. These ripples are incredibly small, stretching and compressing space by tiny amounts. But because pulsars act like such precise clocks, even these subtle distortions can sometimes be detected. A network of pulsars spread across the galaxy becomes something like a vast timing system. Each one sends out its steady rhythm, and by comparing the arrival times of pulses from many pulsars, scientists can search for patterns in the tiny differences between them. It's a remarkable idea. Stars that once exploded in supernovae now serve as tools for measuring the structure of the universe itself. They continue turning quietly, sending out their pulses across enormous distances, and those pulses, arriving on Earth, help scientists understand how space and time behave on the largest scales. Yet despite this extraordinary usefulness, the pulsar itself remains something very simple, a small, dense star, only about 20 kilometers across, spinning steadily in the darkness of space, its beams sweeping across the galaxy again and again, each rotation marking another moment in the long, slow passage of cosmic time. From inside the system, it's hard to see the whole shape, but when we listen carefully to those pulses, those quiet ticks traveling across light years, we begin to understand that the universe contains rhythms far older and steadier than anything in human experience. And the pulsar keeps turning, patient, reliable, its beam crossing the vast, dark ocean of the galaxy, whether anyone happens to be listening or not, mapping the galaxy with pulsars. Once astronomers realized how steady pulsar signals could be, those distant stars began to serve another purpose. They became markers. A pulsar is small, dense, and far away, but its pulses arrive with such regularity that scientists can treat the star almost like a fixed reference point in space. Each pulse is a tiny signal that carries information about the journey it has taken through the galaxy, and that journey can reveal a surprising amount about the space between the pulsar and Earth. When a pulse leaves a neutron star, it begins traveling through the interstellar medium, the vast but very thin mixture of gas, dust, and charged particles that fills the space between stars. Although this material is extremely sparse, it still affects the signal slightly as it passes through. Different radio frequencies travel through that medium at slightly different speeds. This means that when astronomers observe a pulsar, the arrival time of the signal depends partly on the frequency of the radiation being measured. By studying these small delays, scientists can estimate how much material the signal passed through during its journey. And from that information, they can estimate how far away the pulsar is. It may seem like a subtle measurement, but over time, it allows astronomers to build a map. Each pulsar becomes a point in the galaxy whose distance and location can be carefully determined. As more pulsars are discovered and studied, the map grows richer and more detailed. In this way, the quiet pulses from neutron stars help astronomers chart the structure of the Milky Way. They reveal where stars are clustered. They show how gas is distributed through the galaxy. They even help scientists measure how objects move through space over long periods of time. Sometimes, the motion is extremely small. A pulsar may drift across the sky by only a tiny fraction of a degree over many years. But because the pulses are so precise, astronomers can detect those movements. The star slowly shifts its position against the background of more distant objects. Bit by bit, a picture of its journey through the galaxy emerges. And sometimes, the timing of pulsars reveals something even more subtle. If the space between a pulsar and Earth changes slightly, perhaps because a massive object has moved nearby, or because space-time itself has been gently stretched by gravitational waves, the arrival time of the pulses changes by a tiny amount. The difference might be only a few billionths of a second, but that small difference can be measured. This is why astronomers often describe pulsars as natural detectors of cosmic events. Their steady pulses provide a reference signal that allows scientists to notice the faintest disturbances in the universe. Across the galaxy, thousands of pulsars send out their rhythms. Each one is turning steadily. Each one sends a repeating signal into the darkness, and when those signals reach Earth, they bring with them a trace of the journey they have taken, a hint of the space they crossed, a hint of the forces they encountered along the way. It is a quiet form of communication, not a message sent intentionally, but a record of motion and distance written in the timing of the pulses themselves. And by listening carefully to those signals, astronomers gradually learn more about the vast environment surrounding our solar system. A galaxy that, from a distance, may look calm and still, but up close, it is full of movement. Stars drifting through space, gas clouds swirling slowly between them, and small, dense neutron stars turning quietly in the darkness, their beams sweeping outward with each patient rotation. A pulse, then another, each one carrying a tiny piece of the galaxy's hidden structure across the immense distances of space. The slow loss of energy, for all their precision and stability, pulsars do not spin forever at exactly the same speed. Every rotation sends energy outward into space. The beams of radiation carry energy away. Streams of charged particles escape along the star's magnetic field lines. Even the surrounding magnetic field itself slowly releases energy as it interacts with the space around the star. Each of these processes takes a tiny amount of energy from the pulsar's rotation. The effect is extremely small, but over time, it becomes noticeable. A pulsar that rotates once every second today may rotate just slightly more slowly thousands of years from now. The change is gradual, often so slow that only decades of careful measurement reveal it clearly. Astronomers track this slowdown by observing the timing of the pulses. If a pulsar rotates a little more slowly, the pulses arrive just a tiny bit later than expected. At first, the change may be only a fraction of a microsecond, but as the years pass, the difference grows large enough to measure. The star is still spinning, but it is losing rotational energy very slowly. The cosmic clock begins to wind down. This process can continue for millions of years. Even the fastest pulsars gradually slow as their beams sweep across space, releasing energy into the surrounding galaxy. Over long periods of time, the rhythm of the pulses stretches slightly. A pulse that once arrived every second may arrive every few seconds. Eventually, the beam may become weaker as well, making the pulsar harder to detect with telescopes. But the neutron star itself remains. It continues rotating, though more slowly than before. In many ways, this gradual slowdown resembles something familiar. A spinning top, once set in motion, turns quickly at first, Then slowly, almost imperceptibly, its motion becomes gentler. The top continues spinning, but the rhythm changes as energy fades away. The pulsar's slowdown is far slower than anything we observe on Earth, but the principle is similar. The star began its life as a massive sphere of glowing gas. It collapsed in a supernova explosion, its core compressed into an object smaller than a city. And after all of that transformation, it continues to rotate through space, gradually releasing energy with each turn. Yet the slowdown is not always perfectly smooth. Sometimes pulsars do something unexpected. Instead of slowing steadily, they suddenly speed up, just slightly, just for a moment. Astronomers call these events glitches. A glitch is a tiny change in the pulsar's rotation rate, a brief moment when the star begins spinning a little faster than before. The change may be incredibly small, but the precision of pulsar timing makes it possible to detect. For scientists studying neutron stars, these glitches offer an important clue about what might be happening inside the star itself. The outer crust of a neutron star is thought to be extremely rigid, perhaps the strongest known structure in the universe. Beneath that crust lies matter in unusual states, dense layers of neutrons behaving more like fluids than solids. Over time, stresses can build between these layers as the star gradually slows down. When the stress becomes too great, the crust may shift slightly. A sudden adjustment, a tiny rearrangement deep inside the star. And when that happens, the rotation of the pulsar can change by a small amount, a glitch. Then the steady slowdown begins again. These events are rare, but they offer a rare glimpse into the hidden interior of neutron stars. Since we cannot observe those interiors directly, the timing of pulses becomes one of the few tools scientists have for studying what lies beneath the surface. It is remarkable that something so distant and so small can reveal so much. Across thousands of light years, the pulses arrive, each one marking another rotation of a neutron star, and hidden within that rhythm are clues about the forces shaping the star itself. Gravity compressing matter beyond ordinary limits, magnetic fields guiding streams of particles into space, and deep within the star, layers of matter adjusting slowly under enormous pressure. From inside the system, it is hard to see the whole shape of what is happening, but by listening carefully to the pulses, by measuring their steady arrival over years and decades, astronomers begin to understand how these strange stars evolve. Not quickly, not dramatically, but gradually, a slow loss of energy, a tiny change in timing, and the quiet turning of a pulsar continuing through the vast darkness of space. Sudden glitches. For long stretches of time, pulsars behave with extraordinary reliability. Their pulses arrive when expected. Their rotation slows gradually as energy radiates outward into space. Astronomers can track the rhythm of a pulsar year after year, watching the star spin with the calm precision of a distant clock. But every so often, something unexpected happens. The rhythm shifts, very slightly. A pulsar that has been slowing down steadily will suddenly begin spinning a little faster. The change may be tiny, far too small for anyone to notice without extremely careful measurements. Yet, in the timing of the pulses, the difference is unmistakable. The pulses begin arriving just a little sooner than expected, Astronomers call these events glitches. The name sounds almost casual, but the phenomenon itself is deeply interesting. A glitch is a small but sudden change in the rotation rate of a neutron star. Instead of continuing its slow decline in speed, the star briefly speeds up. Then, after the event passes, the gradual slowdown resumes. It is a tiny disturbance in what is otherwise one of the most stable rhythms in the universe. To understand why this happens, scientists look beneath the surface of the neutron star. The outer layer of a neutron star is thought to be a solid crust, an incredibly strong shell composed of tightly packed atomic nuclei. This crust is only a thin layer compared to the entire star, but it forms the rigid outer boundary that holds the surface together. Below that crust lies a much stranger environment. Inside the star, matter exists under pressure so extreme that neutrons may behave like a superfluid, a form of matter that flows with almost no resistance. In this state, the particles move in coordinated patterns unlike anything we see in ordinary liquids. As the neutron star slowly loses rotational energy, the crust and the deeper interior may not slow down at exactly the same rate. The crust, which interacts more directly with the magnetic field and particle winds leaving the star, gradually loses speed, but the superfluid interior may continue rotating slightly faster. Over time, this difference creates tension between the layers of the star. The interior wants to keep spinning quickly. The crust is slowing down, and eventually, the imbalance becomes too large. When that happens, something shifts. The crust may adjust its position very slightly, or the interior superfluid may transfer a small amount of its angular momentum to the outer layers. The result is a glitch. The pulsar's rotation jumps forward by a tiny amount. Then the star settles again into its long, steady, slow down. It is almost like the star briefly clears its throat before continuing its quiet rhythm. These events are incredibly subtle, but they provide scientists with rare clues about what lies inside neutron stars. Because the interior cannot be observed directly, the timing of pulsar pulses becomes one of the few ways astronomers can study what happens beneath the surface. Each glitch offers a small piece of information, a hint about how matter behaves under pressures billions of times greater than anything found on Earth. A hint about the strange physics hidden inside these dense stellar remnants. And even after such a disturbance, the pulsar quickly returns to its steady rhythm. The pulses continue. A flash of radiation arrives, then another, and another, across distances of thousands of light years. The signal carries the story of a star that collapsed long ago, but still turns patiently in the dark, sometimes slowing, sometimes shifting ever so slightly, but always continuing, its quiet pulses marking the passage of time in a way that few other objects in the universe can match. And even these tiny irregularities, these small adjustments deep within the star, become part of the larger story pulsars tell. A story about matter under extreme pressure, about gravity compressing stars into city-sized spheres, and about the subtle rhythms that continue long after a star's explosive ending. Matter beyond earthly experience. Inside a neutron star, the familiar structure of matter begins to fade. On Earth, everything we encounter is built from atoms. Atoms have a simple, recognizable arrangement. A small nucleus sits at the center, surrounded by electrons that move in delicate patterns around it. These structures combine to form molecules, solids, liquids, gases. All light, the materials we see and touch. But inside a neutron star, gravity compresses matter so intensely that atoms cannot survive in their usual form. The pressure is enormous. Electrons are pushed directly into atomic nuclei, merging with protons to form neutrons. What remains is no longer a collection of individual atoms. Instead, the interior becomes a dense sea of neutrons packed tightly together. The particles are squeezed so closely that the empty space that normally exists inside atoms disappears almost entirely. It is a kind of matter that does not naturally occur anywhere on Earth. Scientists sometimes describe the interior of a neutron star as neutron degenerate matter. In this environment, the particles obey unusual rules governed by quantum physics. Neutrons resist being forced into identical states, and that resistance helps support the star against further collapse. In other words, the strange behavior of quantum particles becomes one of the forces holding the star together. Even the outer layers of a neutron star are unusual. The crust may consist of tightly packed atomic nuclei, arranged in patterns far denser than anything we find in ordinary materials. Some scientists believe that deeper layers may form exotic structures, sometimes described with playful names like nuclear pasta, where the shapes of matter resemble long strands or sheets under immense pressure. These strange forms arise because gravity and nuclear forces compete with each other, pushing matter into configurations that would never appear under normal conditions. From the outside, the neutron star appears simple, a small sphere, extremely dense, spinning through space. But beneath that simple exterior lies one of the most extreme environments known in the universe. Temperatures may remain extraordinarily high for thousands of years after the star forms. Magnetic fields twist through the surrounding space. Particles accelerate along invisible paths, and deep within the star, matter behaves in ways scientists are still working to understand, even today. Neutron stars remain one of the few places where theories about the behavior of matter at extreme densities can be tested. Laboratories on Earth cannot reproduce these conditions for more than brief moments. But inside a neutron star, those conditions exist continuously, held together by gravity. In that sense, pulsars are not just rotating beacons in space. They are natural laboratories. Each pulse we detect carries information about the star's rotation, its magnetic field, and sometimes even the interior structure hidden beneath its surface. By studying the tiny variations in pulsar signals, the timing changes, the glitches, the subtle shifts, astronomers gather clues about what lies inside these dense remnants. It may seem like the kind of thing we should already know, and yet the universe continues to reveal new layers of complexity when we look closely. A star collapses. Its matter compresses beyond ordinary experience. Its magnetic field strengthens. Its rotation accelerates. And from that strange combination emerges a pulsar, a small, spinning object quietly sending signals across the galaxy. Those signals travel through the vast emptiness of space for centuries or even thousands of years before reaching Earth. And when they arrive, they carry with them a faint trace of one of the most extreme forms of matter in existence, a whisper from a star that has already lived, collapsed, and transformed into something entirely new, still spinning, still sending its pulses, still marking time in the silent darkness of the galaxy. A wind from a dead star. Although a pulsar is the remnant of a star that has already collapsed, it is far from quiet in its surroundings. The neutron star itself is small, dense, and spinning steadily. But the space around it can be filled with motion. Streams of particles flowing outward at extraordinary speeds. Astronomers call this outflow a pulsar wind. The name may sound gentle, but the wind from a pulsar is very different from the solar wind that drifts outward from our sun. Solar wind is made of charged particles released from the sun's hot outer atmosphere, moving through space at hundreds of kilometers per second. A pulsar wind can be far more energetic, near a neutron star. The magnetic field is so powerful that it accelerates particles to enormous speeds. Electrons and other charged particles become trapped along the star's magnetic field lines, spiraling outward as they gain energy. These particles stream away from the pulsar in a steady flow, and in some cases, they move at speeds approaching the speed of light. The wind carries energy away from the star, helping to explain why pulsars gradually lose rotational speed over time. Each pulse of radiation and each stream of particles carries away a tiny amount of the star's rotational energy. Over thousands or millions of years, those tiny losses slowly add up. But while the pulsar wind drains energy from the star, it also illuminates the surrounding space in fascinating ways. Many pulsars sit within the expanding cloud of gas left behind by the original supernova explosion. The debris from that explosion drifts outward through space for thousands of years, forming large glowing nebulae that astronomers can observe with telescopes. When the high-energy particles from the pulsar wind collide with this surrounding material, they create a brilliant display. The particles interact with magnetic fields and gas in the nebula, producing glowing filaments and swirling patterns of light. The result is something called a pulsar wind nebula. One of the most famous examples lies in the constellation Taurus. It is known as the Crab Nebula. The Crab Nebula is the remnant of a supernova explosion observed by astronomers in the year 1054. Historical records from China and other cultures describe a bright guest star suddenly appearing in the sky, shining brightly even during the daytime for several weeks. Today, the glowing cloud of gas from that explosion still expands slowly outward, and at its center lies a pulsar. The neutron star spins rapidly, sending out beams of radiation and powerful winds of energetic particles. Those particles interact with the surrounding nebula, lighting it from within. In images taken by modern telescopes, the Crab Nebula appears filled with delicate structures, glowing arcs, tangled filaments, and shifting patterns that slowly evolve over time. All of this motion is powered by a tiny object at the center, a neutron star only about 20 kilometers across, spinning, emitting radiation, and driving a wind of particles into the surrounding space. It is a quiet reminder that the death of a star does not bring an immediate stillness to its surroundings. The explosion spreads heavy elements through the galaxy, the neutron star remains behind, and for thousands of years afterward, the pulsar continues shaping the space around it. Energy flows outward, particles race through magnetic fields, nebulae glow with delicate structures of light. Meanwhile, at the center of it all, the pulsar continues its steady rhythm. The beams sweep outward, the pulses travel across space, and somewhere far away, those signals may be arriving at the sensitive instruments of telescopes on Earth. A pulse, then another, each one carrying the quiet trace of a star that once exploded, yet still influences the galaxy around it. The glowing nebula. When a massive star explodes as a supernova, the blast does not vanish quickly. The explosion throws enormous amounts of gas and dust outward into space. This material expands slowly, forming a vast cloud that can remain visible for thousands of years. Astronomers call these clouds supernova remnants. From a distance, they often appear as delicate structures of glowing gas, thin filaments, expanding shells, and faint wisps drifting through the darkness of the galaxy. But when a pulsar sits at the center of such a cloud, something special can happen. The neutron star continues spinning. Its magnetic field accelerates streams of charged particles outward, and those particles interact with the surrounding gas in ways that cause the nebula to glow. The result is something known as a pulsar wind nebula. Inside this kind of nebula, the pulsar acts almost like an engine. Its wind of energetic particles pushes outward into the debris left behind by the original explosion. As those particles move through the gas and magnetic fields surrounding the star, they emit radiation. The light that appears in these nebulae does not come from nuclear fusion, as it does in ordinary stars. Instead, it comes from particles moving through magnetic fields at extremely high speeds. This process is called synchrotron radiation. It produces light across many wavelengths, from radio waves all the way up to X-rays. When telescopes capture images of these nebulae, the result can be surprisingly intricate. Some regions glow brightly, others appear as delicate threads of light winding through the cloud. And at the center of the structure, often hidden within the glow, sits the pulsar itself, the small rotating star powering the entire display. The Crab Nebula is one of the most famous examples. Seen through telescopes, it appears as a complex cloud of glowing gas slowly expanding through space. The nebula stretches across several light years, its filaments drifting outward from the site of the ancient supernova. At its heart lies the Crab Pulsar. This neutron star rotates about 30 times every second. Each rotation sends beams of radiation outward. Each rotation also releases energy into the surrounding nebula through the pulsar wind. If we could watch the Crab Nebula over time, not just as a still image, but as a moving scene, we would see structures slowly shifting. Filaments expand, arcs of light drift outward, waves of energy ripple through the cloud, all powered by the tiny neutron star at the center. It is a remarkable contrast, a vast glowing nebula stretching across light years, and at its center, an object only 20 kilometers across, providing the energy that shapes it. From inside the system, it's hard to see the whole shape of what is happening, but when astronomers observe these nebulae carefully over many years, they can see that the pulsar's wind continues feeding energy into the surrounding cloud. The supernova explosion may have happened long ago, but the system is still evolving. Particles continue streaming outward. Magnetic fields twist through the gas, and the pulsar continues its steady rotation. Again, and again, and again. Each turn sending energy outward into the nebula, each pulse traveling across space. Some of those pulses may have begun their journey centuries ago, crossing the vast distances of the Milky Way before arriving at Earth tonight. A quiet signal, then another, the steady rhythm of a star that collapsed long ago, yet still lights the surrounding darkness in delicate, expanding clouds of light. A rhythm, older than civilization. Some of the pulsars we observe tonight have been spinning for a very long time, long before radio telescopes existed, long before modern astronomy, long before the first cities appeared on Earth. The neutron star that produces a pulsar forms in the violent collapse of a massive star. The explosion of the supernova fades after weeks or months, and the glowing nebula surrounding the star may remain visible for thousands of years. But the pulsar itself can continue spinning far longer than that. Once formed, many pulsars rotate steadily for millions of years. Each turn sends out another sweep of radiation. Each sweep becomes another pulse traveling outward through the galaxy. It's easy to forget that when we detect a pulsar signal here on Earth, we are not observing something happening right now. We are observing something that happened in the past. If a pulsar lies 2,000 light years away, the signal we detect tonight began its journey 2,000 years ago. When that pulse first left the neutron star, the Roman Empire still stood. Entire civilizations have risen and fallen since then. Yet the signal kept traveling across enormous stretches of empty space, through thin clouds of interstellar gas, past stars drifting slowly through the Milky Way, until eventually it reached the small blue planet where our telescopes now listen. A quiet pulse arriving after a journey that lasted centuries. Then another pulse following behind it, and another, because while the signal travels through space, the pulsar itself continues spinning. The star does not pause. Its beams sweep across the galaxy again and again, rotation after rotation, year after year. Even if no one is watching, even if the beam passes through vast empty regions of space, the rhythm continues. This long continuity gives pulsars a special role in astronomy. Because they persist for such enormous spans of time, they become stable reference points within the galaxy. A pulsar can remain detectable for millions of years before its rotation slows enough for its pulses to weaken significantly. During that time, the star drifts slowly through the Milky Way, along with the rest of the galaxy's stellar population, and all the while, its pulses continue marking the passage of time. Some astronomers have described pulsars as the fossil clocks of the galaxy. They are remnants of ancient stars, yet they remain active, quietly sending signals outward long after their explosive birth. The idea carries a certain calm perspective. While human history unfolds over centuries, pulsars continue their rotation across millions of years. Empires rise and fall, languages change, new technologies appear, and somewhere far out in the spiral arms of the Milky Way, a neutron star keeps turning, its beams sweeping across space with each steady rotation. A lighthouse whose light crosses the galaxy again and again. Most of those beams never reach Earth, but some do, and when they arrive, they bring with them a tiny trace of that ancient motion. a small flash of radio energy recorded by a telescope, a quiet signal that began its journey long before anyone on Earth knew what a pulsar was. Yet the pulses continue, each one marking another turn of the star, another moment in a rhythm older than civilization itself. And as long as the neutron star continues spinning, that rhythm will carry on, sweeping silently across the vast darkness of the Milky Way. Somewhere in the Milky Way tonight, countless neutron stars are still turning. Most of them are invisible to us. Their beams sweep across regions of space where no planet waits with radio telescopes listening. Their pulses travel outward into darkness and pass silently through the galaxy without ever being noticed. But the stars themselves continue, small, dense, only about the size of a city, yet carrying the mass of an entire sun. They rotate patiently, guided by magnetic fields that shape streams of particles into narrow beams. Those beams sweep outward with every turn, tracing enormous circles through the quiet space between stars. Pulse, then another pulse, then another. For some pulsars, that rhythm has continued for millions of years. The supernova explosion that created the neutron star faded long ago. The expanding cloud of gas drifted outward and thinned into the surrounding galaxy. New stars may already have formed from the material that explosion scattered into space, but the collapsed core remained, and it kept spinning. At first, the rotation may have been extremely fast, dozens or hundreds of turns each second. Over time, the motion slowed, almost imperceptibly, as the pulsar released energy into the surrounding universe. Yet, even as it slows, the rotation continues, steady, predictable, quietly marking the passage of time in a part of the galaxy far beyond human experience. From inside the system, it's hard to see the whole shape of that story. We notice the pulses arriving at our telescopes, brief signals traveling across thousands of light years. But those signals are only tiny glimpses of a much larger process. A star lived, it burned its fuel. Gravity pulled its core inward. The explosion scattered its outer layers across the galaxy, and the remnant became a neutron star, spinning slowly in the darkness. What began as the death of a star became something else entirely. A beacon, a cosmic clock, a small object that continues to send its rhythm across space long after the original star disappeared. Across the Milky Way, many such clocks exist. Some rotate once every second. Some spin dozens of times each second. Some complete hundreds of rotations in the time it takes to blink. Their beams sweep across the galaxy like distant lighthouses, turning through a silent ocean of space. Most of the beams pass through empty darkness, but every so often, one of those beams crosses the path of Earth, and a radio telescope listening quietly to the sky records a pulse, then another, each one marking another turn of a star that collapsed long ago, each one carrying the trace of motion that has continued patiently across centuries. It's easy to imagine the universe as a place of dramatic explosions and powerful events, and those things do happen. But the story of pulsars reminds us that the universe also contains quieter rhythms, processes that unfold slowly, objects that continue moving long after the moment that created them has passed. A pulsar does not hurry. It simply turns again and again and again, and somewhere far away in the dark, one of those small stars may still be spinning tonight, its beams sweeping across the galaxy in the same calm rhythm they have followed for millions of years. If your mind is beginning to drift now, that's perfectly fine. You don't need to hold on to every detail of the journey we've taken tonight. The pulses will continue whether we remember them or not. The neutron stars will keep turning, and the quiet signals will keep traveling through space, crossing the galaxy long after this moment has passed. So you can let the story fade gently now. You can let the distant stars continue their slow motion on their own. And if sleep is already finding you, you can simply allow it to arrive. There is nothing more you need to do now.